When I was a kid, I heard a fable called The Crow and the Pitcher. The clever crow drops stones into the bottle. The water level rises and it gets to drink. This story taught me a lesson from an early age. Stay hydrated, kids. But recently, that childhood belief got completely shattered. Because I discovered the crow actually can't drink the water at all. Let's do an experiment. Aesop's Fables doesn't specify the shape of the bottle. I grabbed a few random bottles and put in a little water. Remember, you're a crow. You don't have hands. You can only use your beak to drop stones into the bottle. Let's give it a try.
Where's the water? This whole thing was a scam for crows. Scammed again, crow.
All scams against crows. The water level rises a bit, then stops halfway. Dropping more stones is just pointless. The crow would have died of thirst 8 times over. With this cylindrical bottle, the water level rises a bit higher. With this inverted cone container, the wider it gets at the top, the harder for water to rise. So there's no way the crow could drink from it. What are you laughing at now?
That huge bowl, the crow could literally just dunk its head in there.
But I found that the water level in a conical flask rises quickly. The crow can actually drink the water. But the question is, where would you normally find a conical flask? A chemistry lab. If you're a thirsty crow flying into a chemistry lab, honestly, you're better off staying thirsty. Turns out childhood stories really do lie to us. If you want your kids to grow up fast, just subscribe, Bidao. Wait a minute. Are the stones the crow drops really completely useless? Let's re-examine this problem from an academic research perspective. The reason the crow can't drink the water is there are many gaps between the stones. When the water level rises, it fills these gaps first. It's hard for it to reach the bottle's mouth, but Aesop's Fables doesn't specify how the pebbles are arranged. If we can pack the pebbles more densely, we can reduce the gaps and the water level will rise higher. Let's simulate how pebbles stack up in the bottle. Assume the pebbles are ideal uniform rigid spheres, and the crow is an ideal crow with a degree in civil engineering capable of arranging the pebbles into any structure. As early as 1611, astronomer Kepler proposed the Kepler conjecture for the crow. He believed the densest sphere packing in space looks like this, one next to another. Similar to the way grocery stores stack oranges. In the bottom layer, each sphere is surrounded by 6 others. This creates a dimple between every 3 spheres, then each layer sits in the dimples of the layer below. Looks pretty tightly packed, right? This dense packing method is everywhere in life, like magnesium atoms, copper atoms, freshly fried sesame balls, fish balls, and hot pot. So if the crow stacks the pebbles in this structure, it can be viewed as repeating arrangement of a parallelepiped unit cell. We learned the 7 crystal systems and 14 Bravais lattices in structural chemistry back in 2nd grade. We call such a repeating unit a hexagonal unit cell, and this type of packing is called hexagonal close pack. We can easily calculate that the pebbles occupy p divided by the square root of 18, about 74%. The voids account for 26%. So only if the water level in the bottle is above 26%, does the crow have a chance to drink? This packing method intuitively feels so simple that it can't get any denser. But mathematicians actually spent 400 years using a 121-page paper, plus computers to finally prove in 2017 that there's no denser packing method in space than hexagonal close pack. I'm just saying. The fruit stand lady stacks her oranges like this every day, probably proving this sphere packing problem.
Right.
So if the water level is below 26%, the crow would just die waiting? No way. The crow can find cubic stones with no gaps at all, as long as there are no gaps. No matter how little water there is, the crow can drink it. Any crow that's been through 2nd grade should know 3 dimensions tessellation. It can find many truncated octahedron stones that also pack tightly. Easy peasy, get that water. It can find truncated cube stones and regular octahedron stones, then pack them tightly in a 1.1 ratio. Easy peasy, get that water. Or find regular octahedron and tetrahedron stones, pack them tightly in a 1.2 ratio. Easy peasy, get that water. Or find great rhombic-octahedron stones and octagonal prism stones, pack them tightly in a 1.3 ratio. Easy peasy, get that water. If you think these stones are hard to find, the crow has even more options. If it finds these 3 types of stones, it can also easily get that water. The smartest crow can try collecting 4 types of stones, pack them tightly like this in a 1.1 3.3 ratio. Still easy peasy, get that water, see? Knowledge opens doors. Ignorance leaves you stuck. Some viewers might say, your method isn't practical. Sure, I can understand there being crows that study topology, but where in real life would you find so many different shaped stones? I fell into deep thought. Does the crow have any other options? Aesop's Fables never said what dimension the crow was in, so if it's a crow from a higher dimension facing a higher dimensional bottle, would it then be able to drink the water? Let's say the pebbles are also high-dimensional spheres. Although we in 3D space can't visualize high-dimensional spheres, the problem becomes quite simple. We just need to study what percentage of high-dimensional space can be occupied by spheres in their densest packing. This problem tormented several generations of mathematicians. Finally, in 2016, Ukrainian mathematician Marina Vyazovska rigorously proved that spheres in 8-dimensional space, when densely packed, occupy pi to the 4th power over 384 of the space volume. A week later, she cracked the 24-dimensional case, shocking the math world. Inception even wanted to invite her to write the sequel. The paper is linked here. Should help you think this through better. But what I didn't expect was, although mathematicians have calculated the volume ratios for sphere packing in 4D through 7D space, the rigorous proof remains an unsolved mystery to this day. If you're interested, you can give it a shot. The results are truly amazing as dimensions increase. The proportion of space that densely packed spheres can occupy gets smaller and smaller. Even in 8-dimensional space packed full of spheres, they only occupy 25% of the volume. In 24-dimensional space, spheres packed together only take up 0.2% of the space. That's pretty hopeless. The higher the dimension the crow flies into, the less likely it can drink the water, so there's only one option left. A dimensionality reduction strike straight out of sci-fi collapsed the water bottle and itself directly into 2D space. The densest packing of circles in a plane can reach this way. With just over 10% water volume, our flattened little crow finally gets a sip. Many people might think, the crow drinking water problem in high-dimensional space is meaningless. But when I was reading the literature, I found this problem can actually help with automatic error correction in data transmission. I'll save that rabbit hole for another video. If you're interested, we'll do a dedicated video on it later. Today, we systematically analyze the crow and pitcher problem. Actually, if you think about it, those stories we've heard since childhood, do they really have just one ending? The fable of the crow and the pitcher teaches us to learn from the crow to think outside the box when facing problems. But when we think outside the box about the fable itself, it actually contains unsolved mathematical problems from the past few centuries. If I ever tell this fable to my kids, I'll tell them the crow didn't just think of dropping stones to get water. It also had to consider the densest sphere-packing polyhedral combinations and the limits of high-dimensional space. This is the real crow from the famous fable Crow's Spirit. Alright, thanks for watching this video. If you've discovered any truths after growing up, feel free to leave a comment and let me know. Don't forget to like, subscribe, and hit the bell. See you next time.